Yeah, let's go ahead and pick it back up again. So next up we've got Lucas Fish, who's completing a master's project, supervised by Tom States. So please take it away.
Okay, hi everyone. Please call out like questions or anything if it's not clear. I'll try to explain further. So for the past year, I've been working on a project titled Universal Scaling of Hypergraph Product Codes, so like on error correction type stuff. So first of all, why might that actually be useful or important? We're kind of at the forefront right now of where quantum computers are becoming usable. Even this year, Google did like the first experimental paper, showed that like scaling out quantum error correcting codes, you get like an exponential decrease in failure rates. And for useful problems to be able to be solved, we need quantum computers to be scalable and fault tolerant. And for both of those things, you need like good quantum error correcting codes. And it's highly non-trivial to actually design good quantum error correcting codes. You can borrow some stuff from like classical error correction, but there are some uniquely quantum problems like the no cloning theorem that means you can't directly use it. And thus we arrive at the need for quantum error correction. Have you guys all heard of stabilizer formalism?
No.
No? Okay, cool. So basically stabilizer formalism is a way to think about quantum mechanics where we have stabilizer measurements, which are projected measurements onto a subspace of your Hilbert space, but not necessarily onto a single state. So for example, take just like the Hilbert space of 2 qubits. We have 2 stabilizers, which forms a group that spans the whole Hilbert space, which is sigma z on qubit 1, tensor product with sigma z on qubit 2, and that projects an arbitrary state onto one of 2 subspaces in our Hilbert space, which is the span of 0, 0, and 1, 1, and 0, 1, and 1, 0. And so quantum error correction basically can be just distilled down into the following idea. As long as we keep our states involved in computation in a stabilized subspace, that is, anytime we measure a stabilizer, we just get a +1, then any errors that might bring our state into a superposition of plus and -1 for our stabilizers are discretized in the sense that when we measure a stabilizer, we either get a +1 or -1. If we get a +1, then that means that our error has actually been mitigated, so an error hasn't occurred. And if we get a -1, then we know an error has occurred and we can apply error correction. And the reason why we want to use stabilizer measurements instead of actually measuring physical qubits is that when we measure physical qubits, it collapses superpositions, right? That's like an axiom. So yeah, that's basically how we can think of quantum error correction. And one of the first topological quantum error correcting codes, which I'm sure some people here know, is the torque code. And so for the torque code, basically we stick a bunch of physical qubits onto a 2D lattice, like down there. So the yellow dots are like your physical qubits, and they sit on a lattice, and the lattice has periodic boundary conditions in the horizontal and vertical directions. So that's like the topology of the torus, like a donut. And so for that lattice of qubits, we define 2 sets of stabilizers, which are vertex and plaquette stabilizers. So the vertex stabilizer, basically pick a vertex in that lattice, for example here, and your stabilizer is going to be sigma x on the 4 nearest neighbors of that vertex, so that guy there. And then for a plaquette, it's kind of the same thing here, only we pick a face of that lattice, and our 4 nearest neighbors form this little like face shape, and it's sigma z's instead of sigma x's. So we have like X-type stabilizers and Z-type stabilizers. And again, our code space, so that is like the logical states of our quantum error correcting code is the simultaneous +1 eigenstates of all of those stabilizers. So that's just like general for stabilizer codes. And the cool thing is, so we have all these physical qubits, but and arbitrarily you can like scale it up, right? You can make the lattice as big or small as you want, but it's always going to encode 2 logical qubits in this lattice. So we can scale it up, but we'll always have 2 logical qubits. And so we have our code, it's in some logical state that we define to be our code word. And you might get some physical errors that might like flip one of the qubits, right? It sets a 0 into a 1. Or you might get like a phase flip. So it might go from 0 plus 1 to a 0 minus 1, right? Now, whenever a physical error acts on our code space, and then we measure all of our stabilizers for a toric code, suppose you have some bit flips that act along this little string of physical qubits. When you measure those stabilizers everywhere, you'll get plus ones except at the endpoints of your strings. And so like from a condensed matter physics perspective, you can consider that as like an anyon excitation. So you get like two little -1 stabilizers that like move around on your lattice. So we'll get like a -1 if we measure this plaquette stabilizer and a -1 here. And so how we actually error correct that code, which is unique to the Tor code, is you just have to close this little loop. So we measure a -1 here, a -1 here, and all we have to do is apply bit flips here and down, and then you see that it's like closed this little green loop. So that's forming a homologically trivial error class, which means that it acts trivially on the code space, and we've corrected the error successfully. Now, you might think, what happens if we try to close it by going around the periodic boundary? That would be failed error correction, because that's actually applying a logical operator. So our logical operators for like a Tor code wrap around the torus, around this way or like this way. And the trivial errors that don't affect the code space are just kind of like, it's like little strings that like sit on the torus.
Can I ask, if it's periodic boundary conditions, how do you know which way is like the wrong way? Isn't it topologically the same? Like, can't you connect, you know, what's the difference between connecting those two things going the other way versus the green line that you've got there? Oh, versus the one you.
Oh, you mean like if you go this?
Yeah.
So it's to do with the homology class of the torus, whether or not you can like contract that cycle down to a point. So like if you have like a donut and then you have like a string that wraps around the edge of the donut, you can't contract to a point, right? Like if you kind of slide it around.
So it's the fact it's a 2D,
yeah.
Okay.
Yeah, exactly.
Okay.
So sorry, the logical qubit is encoded in those two aspects. Of
Yes,
the
around the winding number. So the logical operators are actually topologically distinct from like little trivial errors strings that like, don't do anything. And that's the crux of topological quantum error corrections, like that it has to be defined by like the homology classes. I can explain that later, maybe. Now, so another way to look at that Tor code is actually that our code space can be considered the degenerate ground state of like an Ising type Hamiltonian, where we sum over the vertex operators, vertex stabilizers, and the plaquette stabilizers. So from before, see like there's however many vertices on that little graph, and there's also however many like faces. So really we can consider a Hamiltonian that's just like summing over all of those little stabilizers. And by mapping it to that, considering it as like the ground state of that Hamiltonian, we can map it to a random bond Ising model, where it's just like a normal Ising model, except our coupling constant goes from like a -1 to +1. So ferromagnetic or anti-ferromagnetic couplings, where the probability distribution of that ferromagnetic or anti is given by this like number p, where that's just like the probability. And so when we map the Tor code to a random bond Ising model, that probability here of whether or not you're in the ferromagnetic or anti-ferromagnetic for one of those couplings corresponds to like the probability of a bit error, like a bit flip occurring on any of those physical qubits. And so with that map, we can use some cool condensed matter stuff to show that there's a phase transition in the random bond Ising model where we get like same spin grains. And that corresponds to like a threshold probability for our quantum error correcting code. So for that quantum error correcting code, when we're above that critical threshold, then the code's just useless as we scale it up. But as long as we're below that like phase transition, then by increasing the size of the lattice, we can exponentially decrease error rates, which is really cool. That's like good stuff. And so there's like an empirically motivated hypothesis that you get universal scaling, similar to like statistical mechanics stuff, where your probability of failure, so for the code's error correction to fail, is just a function of the length of your lattice, so the side length, divided by the correlation length, which is that like, roughly you can think of it as like the average same spin grain size in our like Ising model. And then because we are expected to get exponentially decreased failure rates, we end up with this kind of formula here for the probability of error correction failure. And we get a universal scaling regime. But the problem is, in that regime, when our probability of error, physical errors like on each of the qubits is sufficiently small, most of our stabilizer measurements are just trivial. We just get +1s like everywhere. And then the endpoints of the few little error strings that occur, we get -1s. But when we're in this regime, like most of our stabilizer is just like useless. We're not really getting anything out of it. So like from an information theory perspective, it's like not optimal in this regime. So if you haven't seen information theory stuff much, I'll give like a little primer. So suppose we have two random variables, x and y, where x might represent a transmitted code word. So we encode some logical state onto our Tor code. And then y is that state after we measure something sometime later. So the channel in this case is just like time actually passing. And so the more information that x has, that random variable, the more surprised we are to discover its value. And you can quantify that through the Shannon entropy given by this guy, where p is just the probabilities associated with each outcome, and variable x. And we can also talk about the mutual information of two random variables. So that's how much we know about x after we learn the value of y. So in the context of like transmitting a code word and receiving it, the mutual information is like, okay, we send x, and then sometime later we measure y. How much can we reconstruct x knowing the value of y? And that's given by this formula here, where it's like a double sum over joint probabilities and marginals. Is that okay? Does that make sense? Okay. So we propose a mutual information as a quantum error correcting optimality metric to compare different like code families. And there were a few hypotheses we came up with and have proved like 2 of them. So firstly, in the limit as the probability of bit flips on each like physical qubit goes to 0 and our lattice gets infinitely big, that mutual information goes to 0. The mutual information of the syndrome, so that's the little stabilizer measurements, and then the error correction success, so whether or not we've actually corrected it successfully. So this is like our new metric for code optimality. And the second hypothesis is that for a given code family, there's a code length that maximizes that mutual information. And we can consider such a code optimal. So this graph here, this is just a classical repetition code, where we represent like a logical 0 as just a string of zeros, 0, 0, 0, 0, and a logical 1 as a string of 1s, 1, 1, 1, 1. And you can see that as we scale that code up, where n is just the number of bits that we're encoding our code words as, the mutual information of syndrome and error correction first increases, and then it decreases and eventually goes to 0. And this is at different probabilities of error on each of like the bits. And so you can see that as the probability approaches, like gets higher and higher, then you need to have your code bigger and bigger to maximize that mutual information. And finally, we suppose that we can choose different codes with weight W, that is like how many physical qubits our stabilizers actually act on, and also the distance of our code, so that's like the size of the lattice. We can tune both of those to maximize our mutual information, which is like our proposed optimality measure.
Can I just check I understand what you mean?
Yep.
So what you're saying is if I have a certain number of qubits, I want to split them up into these size things so I get maximum sort of.
Yes, exactly. So we want to get as much information as we can.
So you don't want to waste physical qubits and only having a few logical qubits. Okay.
Exactly. Yes, that's exactly the idea. Okay, so here's a way that we can kind of generalize. So we have that Tor code and it works really well. It has like a high threshold, etc. That's like what everyone's doing right now. I think like Google, IBM, doing like Tor code stuff or surface codes, which is like similar. But how can we actually generalize that to try to like compare different code families? The hypergraph product is a way that we can arbitrarily construct a quantum error correcting code, taking 2 component like factor classical codes, and we take this hypergraph product and it creates like a quantum error correcting code. So first of all, for classical linear error correcting codes, we describe them by a Tanner graph, which represents the parity check matrix where the parity check matrix is defined such that the code space is the null space of that. So for example, just take a parity check matrix like this guy, and then if we multiply some vector, and that vector is our code word, if it's a code word, then that product is going to be 0. So take the parity check matrix, it acts on our code word and gives you 0. And if you have an error, then you're not going to get 0. So errors, when you act the parity check matrix on it, you get something that's not 0. And so the Torah code can actually be constructed as the hypergraph product of 2 classical repetition codes, which is really cool because it's like the simplest possible quantum error correcting code you can make from this construction. And so how do you actually make the Torah code? Here's just the Tanner graph of a repetition code. Here's the Tanner graph of another repetition code. And the hypergraph product forms this kind of shape where your edge type, so that defines like the type of stabilizer you're doing, whether it's an X or sigma X or sigma Z. Yeah, I'll skip over this just in the interest of time, but I'd be happy to talk about it later. So an idea we had to generalize the Torah code is that the repetition code has a Tanner graph that looks like this, where each stabilizer just acts on 2 little bits. And so we thought we can just generalize it by instead of having it act on like 3. So here's like the simplest possible way to make higher weight stabilizers for quantum error correcting codes. So like instead of just doing 4 nearest neighbor qubits in the Torah code, you can go to like 6 or 7 or 8 or however many you want. How we actually simulated all this stuff, I found the best way to do it. The problem is like if your quantum error correcting code gets sufficiently large, then your probability distribution space of all possible like stabilizer measurements and errors scales exponentially. So it just becomes impossible to do anything analytically. So we rely on Monte Carlo methods, and there's a really cool way that came from Bayesian inference that I found, where you can estimate Shannon entropy using this thing called a Pitman-Yorn mixture, which comes from statistics, I think. And so I use that, and also I use this generalized decoder called a belief propagation with ordered statistics decoding for actually like decoding it. So we do a bunch of Monte Carlos, we decode the thing, see if it was successful in actually error correcting, and then measure what that mutual information was to be able to compare code families. So we denote our codes by our lattice side length L, so that's just like how big that lattice is, and kernel weight W, so that's how many bits our stabilizers actually act on. And we fix our probability of errors occurring on each physical qubit, and we fix a number of logical qubits. So for reference, the Torah code encoded 2 qubits, but like it changes as you change the code. And we compared the mutual information and the probability of failure across code families, where these are some dimensions for just the codes considered in this work. And what we found is that, so the solid line is the mutual information, and that goes to the left axis, where the x-axis is like your actual number of physical qubits, n, and the right axis is your probability of failure. So that's like, what's the probability that your error correcting code is actually failed at correcting the error? What we found is that at fixed bit flip probabilities and fixed logical qubits, picking the code family that had the highest mutual information actually corresponds to lowering the probability of error. So you can actually use this quantity, that ISEC, as an optimality metric. So you can compare different code families in this universal scaling regime in order to figure out like which one has lower probabilities of error. So it's like an interesting metric that you can kind of use to compare code families. And these are just some graphs of some four logical qubits, and this is 9. Where to go next is to look into more general low density parity check constructions. So there's a bunch of cool stuff from literature, how to construct new codes. I only consider the hypergraph product construction in this work. Also to improve the Shannon entropy estimator, which is like an open problem in literature. It's really hard to estimate entropies given like really few samples from that distribution. And another cool idea is to consider the time evolution of quantum algorithms as a 3D foliation of 2D quantum codes. So you get like this 3D code that represents like one axis is time. And we want to check whether like you can identify optimal codes by maximizing that mutual information metric over like a 3D volume element. And finally, we want to analytically prove the conjecture of like, does maximizing that neutral information actually correspond to like minimizing the logical error probability? And that's it.
Thanks, Lucas. Yeah, we've got plenty of time for questions because the next talk is at 1:30. So let's start off here, right? So that the last aspect you were talking about the 3 dimensions, right? Where you have time. So I guess like sort of normally think about time as being like sort of trivial evolution, right, for your system. So do you expect that there's a big difference between like, I don't know, I guess it would be the rate at which errors occur in time and how different codes handle them? So
Yeah, the idea is like if you have time varying error channels, then it might be different. But assuming that you have just like the same identically distributed independent errors, it's possible that it's just the same thing. Like maximizing over one sheet is just like the same. Well, yeah, it's just that's more from my supervisor. I actually don't really know too much about it.
the other question.
I'm sorry, I got a bit confused. So if you had to summarize what you've achieved in your project so far, what would you say?
I found a new mutual information metric that, and no one's done this before. No one's looked at this mutual information stuff. And it seems like it corresponds to being like a useful metric.
So the proposal that this is a good way to sort of optimally choose your qubits looks like it might work out.
Yeah.
And you have some evidence.
Yeah, I have lots of results.
There's other things to check.
Yeah, I'm like still doing it all kind of last minute, but yeah, lots of results.
So did you say you hope to analytically prove it? So you're sort of doing numerical demonstrations?
Yeah, so far it's just been all numerical. Even in the case of like classical error correcting codes, because it's all like huge combinatorial arguments.
Sure.
Yeah.
So do you think there's a hope of doing it analytically, or is that just pipe dream?
If I was good enough at math, maybe. Yes, we'll see.
Well, I guess have things like this been done before? Because I mean, analytically doing stuff like this sounds like it's proving P versus NP hard type thing. No, it's reasonable to
relying on statistical mechanics probably has like more likelihood than just try to brute force the math. There's a lot of really beautiful like statistical mechanics mappings that you can make with those like using models and stuff.
Okay.
Hopefully for that,
Sorry, ask one more question. So the Tor code is good for 2 logical qubits. So is there any like approach to using that code on more than 2, like concatenating parts of a lattice or something, or what is the actual?
Yeah, so if you take like a Tor code, if you puncture it, you can increase the number of like logical qubits. So like literally just make a defect, like take out 1 of the qubits, or you can also just like stick them side by side, and then you have like independent copies.
Mm-hmm.
And then in that case, then the problem is like your probability of failure is if any of the component codes fail, then the overall thing fails.
Right.
So that's kind of like suboptimal as well.
Yeah, okay. But maybe last question.
Can you show me the slide, the very first one, when you had the graph that extrapolates like the linear, how many years? Yeah, this is this the data points are more or less real kind of thing, and then
I took that from someone's lecture. It's not my work.
okay.
Take it with a grain of salt. Maybe.
So let me now extrapolate it when it crosses the upper line into the 6 qubits you need for usefulness threshold. That will be 2040. It's more.
Maybe 50.
Okay. No, thanks.
All right, let's thank Lucas for. All right, for setting up for the next talk,